Now for section 12.2, we're going to move into what we call an inverse. We're going to learn how to use some special keys that we have on our calculator. And then we're also going to call a one-to-one function when each x value corresponds to just one y value, and each y value corresponds to just one x value. Let me explain that as a graph. What we mean is that every x value on our domain is used only once. That's what makes it a function. Every x value is used only once. Now we're going to make it a one-to-one function. Also, remember the domain, any number on the domain, which you should call the x value, is used only once. That makes it a function. Now it is called a one-to-one function where every value on the range, which is usually a y value, every value on the y is used only once. I see that it is a function because my numbers on my domain are used only once, but it is not a one-to-one function because there is a value on the range, 7 in this case, that it is used twice. Remember, in order for this to be a function, the domain values can only be used once. In order for this to be a one-to-one function, the values on the range can only be used once. Now we see on example B, values of the domain are used only once. The values of the range are only used once each. So that's what we call a one-to-one function. Now we're going to start using a symbol for inverse. It looks like an exponent to the -1. Now that is not an exponent. It just looks like an exponent, but that is how we call the inverse. So the inverse of a function, or the inverse of a one-to-one function, f, it is written as f to the -1. I said it looks like an exponent, but it is called the inverse function. It is all the set of all the order pairs of yx, where xy belongs to f. All that this thing says is the x and the y values switch places. The inverse is formed by interchanging the x and the y, so the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. All right, with that mumbo jumbo said, when it is a one-to-one function, just change the values of x and y. And that is the inverse. Let's take a look at this as an example. First of all, it says, decide whether each function is a one-to-one. If it is, find the inverse. So first of all, I want to make sure it is a function. It says it is a function because it says decide whether each function. So it is telling me it is a function. And then the way I know it is a function, because I look at the x values and I can see that they are used only once. So it is a function. I kind of knew already because it says decide whether each function. It was telling me it was a function. But that's how you check if this is a function. Now it's asking me, check if it is a one-to-one function. So now I'm looking at the y values. And I'm making sure they are used only once. I have these 2 points. They have the same y value. And then I have these 2 points that have the same y value. So I see that there are 2 points that have the same value. As a matter of fact, there are 2 pairs that have the same y value. So I'm just going to say this is not a one-to-one. So decide whether each function is one-to-one. Not a one-to-one function. It is not. Now it said if it is, if it was a one-to-one, find the inverse. All I'm going to do for the inverse, I'm going to switch the x and the y places. But this is not a one-to-one function, so I stop. Now looking at B. First, I'm going to check if it is a function. I'm pretty sure it is going to be a function because it was said it was a function. How do I check it is a function? My x values are used only once. None of them repeat. So yeah, I see that it is a function. Now, how do I know? Now that I know it's a function, how do I know it is a one-to-one function? I look at the y values. And yeah, None of them are used more than once. So now I know, yes, it is a one-to-one function. So if it is, find the inverse. And I'm just going to call this G inverse. So it looks like G to the -1, but notice I called it G inverse. The G inverse is going to be the set 1, 3, 2, 0, 3, 2. Notice how on each point, I'm just changing the X and the Y values. So you can pretty much imagine what I'm going to write for my last point. Remember, all I'm doing is the X and the Y value are switching places. So I'm going to call this 0, 4. Now, why do we call this a one-to-one function? Because the inverse, once I did the inverse, it remains a function as well. On example A, if I would have done the inverse, let me just do inverse of 2 points. If I would have done the inverse, it stops being a function. Remember, a function, it is a set where the X values are used only once. So once I do the inverse, it stops being a function. That's why in example A, we called it not a one-to-one. Now you try some at home. This is what you guys should get. For example B, I will say, take a look at those 2 points. That's why I call it not a one-to-one function. Now, if we have it as a graph, if we have the pictures, one thing is one-to-one function will pass what we call the horizontal line test. Looking at my example A, look, I did a horizontal line that touches my function more than once. In this case, 3 times. Because it touches it more than once, it is not a one-to-one function. Why? Because in this case, those points have the same Y value. Now look at example B. I did various, well in this case 3 horizontal lines. There's 1, there's 2, there's 3. In each case, I cross my graph only once. Right? If we have the graph and we can come up with at least one line, doesn't have to be that many, at least one line, one horizontal line that touches my graph more than once, it is not a one-to-one function. If I cannot come up with a line that touches my graph more than once, it is a one-to-one function. Now, some people might say, well, what if I come up with something like this? I touch it more than once. Yeah, that's not a line. That's some curves. Remember, a line is something straight. So no, we cannot do that. Now, how to find the equation of the inverse? First of all, interchange the X and the Y value. The X and the Y value are going to switch. And then solve for Y. Your result, replace it with F inverse of X. So an example, decide whether each equation represents a one-to-one function. If so, find the equation that defines the inverse. Now this thing, 2x plus 5, remember, you guys might be familiar with the formula y equals mx plus b, where that gave us the line. M was what we call, the number in front of the x, what we call the slope. It told us how to move. The number at the very end, we called it the y-intercept. So that's where we start on the y-axis. We use the letter B because that's where we begin when we start graphing. That is the idea that I have here. I see the slope is 2, the y-intercept is 5. I know that gives me a line. It's a non-vertical line. So yes, that's definitely a one-to-one function. Now, let me find the inverse. What I'm going to do, instead of f of x, let me write this as a y. So I have y equals 2x plus 5. So instead of f of x, g of x, or anything that I have, I'm going to replace it with a y. Now, what I'm going to do is the x and the y are going to switch places. I have x equals 2y plus 5. So the x and the y switch places. Solve for y. So get the y by itself. I'm going to get rid of this plus 5 by subtracting it on both sides. So I have x minus 5 is equal to 2y. To get the y by itself, let me divide both sides by 2. So I'm going to have y equals x minus 5 all over 2. I'm fine with that. If you guys are writing this on paper, I'm fine with that. Now, my math lab might say you must separate them. You must separate this as y equals x over 2 minus 5 over 2. Notice how it is the same thing. It's just that a fraction got split. But it is the same thing. And some people might even go, well, can I write this as y equals 1/2 x minus 5/2? Because they took the x out of the fraction? Sure. Those three things, those three examples are basically the same thing. So yeah, that is the inverse. Now, let me erase my work here. How am I going to write this? I'm just going to write this as f inverse of x equals, obviously I'm going to do one of these. Let me just write this as x over 2 minus 5 over 2. I'm just going to choose one of the three ways how to write it. I said all those three equal the same thing. I'm just going to choose one of them. Now, example B, y equals x squared plus 2. The x squared, we've worked these. Remember, we learned how to do everything to the second power. That looks like a parabola that it's open up. I have a graph that looks like that in my mind. Now, looking at that, I can say, well, yeah, that for sure is not going to pass the horizontal line test. I can think of a line that touches my graph more than once. So by all means, it is not a one-to-one function. So it's not a 1-to-1 function. Right, it failed the horizontal line test. Now, for example C, to the third power looks something like that. Yeah, that's definitely going to pass the horizontal line test. So how am I going to find the inverse? First of all, let me write this as y equals, right? Instead of f of x, I'm going to write this as y. Y equals x minus 2 all to the third power. Let me solve for y, but first let me switch the x and the y. I have that x equals y minus 2 all to the third power. All right, so we have to get the y by itself. I see an exponent. I see to the third. I know before when we had a second power, remember, if you guys think of it, how did we get rid of a second power? We did a second root. We did a radical. Radicals and powers undo each other. When it was to the second power, I did a square root, right? Because the radical was 2, or the inside, the power was 2, an exponent. So for power of 3, I'm going to do a cube root. I'm going to say the cube root of x is equal to y minus 2. Now, notice how I did the cube root because my power was 3. So y is going to be equal to the cube root of x plus 2. Notice how that it was y minus 2, so I moved the 2 over. But notice how I put it outside of the radical. So I'm just going to rewrite this as f inverse of x is equal to the cube root of x plus 2. Now let me show you something really quick. You don't have this slide. As a matter of fact, what I did was, even on the second example where I said it was not a one-to-one function, I did the inverse of each. So you don't have this slide. It is just, I want to show you guys things out. We said that the first one was going to look like a line. It was going to intersect at 5. The y-axis is a 5, and my slope was going to be 2 over 1. And we figure out the inverse was x minus 5 over 2. Now, here, you guys see in red, I have the original function, f of x. Let me graph f inverse of x. Now, since the x and the y were switching places, let me also draw the line y equals x. So in red, I have f of x. In blue, I have f inverse of x. And in green, I have the line y equals x. Okay, I'll come back to this thing. Let's take a look at the second one, x squared plus 2. We know it's a parabola, it's open up, it moves 2 up. We know the vertical shifting. Now for the inverse, I do the positive square root and I do the negative square root, and I get that, right? That's the graph. And then in green, let me do the line y equals x. Now for this other one, there's the line, the f of x in red. Let me do the f inverse of x. And let me also do the line y equals x. You might be thinking, why is the line y equals x important? Now, what the line y equals x does is that it reflects everything. Everything reflects on that. This point reflects right here. Think of that as a mirror. Everything reflects, right? If I was to fold my paper along the line y equals x, if I was to fold it along the green line, those 2 points will overlap. The same thing with this point and this point. If I was to fold my paper along the green line, the 2 points that I just marked will overlap. Same thing on my second example. These 2 points overlap. These points will overlap. And obviously, as you guys can see, these points will overlap. Now, the interesting part is, you guys will notice on my first and my third example, what happened if the line is on the point, the original point, it is on the line y equals x. So what if it's on the green line? If it overlaps the green line, if I was to fold it, I get the same point. Notice how the f of x and f inverse of x intersect at that point. Okay. Something I wanted to graph. So now let's show you guys. So now going back to the slides that you guys have, this is what you guys should try at home. These are a few examples for you guys to try at home. And then that's all we have. The same thing with your graphs though. I want to show you guys graphs on your, these examples. You don't have this next slide at home. You don't have this one. But on my first one, that's f of x. That's f inverse of x, and that's the line f of x. Notice how they reflect the line y equals x. Looking at this other one, that's f of x in red. In blue, I have f inverse of x. And in green, I have the line y equals x. Same thing here. That's f of x. That's f inverse of x. And the line y equals x. Once again, the line y equals x is where they reflect. So now what you guys have on your PowerPoint is, if I have the line y equals x, this point and this point, they reflect. The a and b switch places. That's what we call the inverse. They reflect. Have this other one right here. So matter of fact, if I was to graph these, that's how f of x looks like. The in red is the f inverse of x, and if you guys imagine the line y equals x, see they will be reflecting. That's another example that this is how the book shows you guys how the original function and the inverse, they look like a reflection across the line y equals x.